Hello everyone, my name is Thomas Urban. I'm member of a systems engineering team for automotive powertrain systems based in Germany, and I like to talk about some basics of functional safety for automotive. What you learn is some terms, acronyms, concepts, what is an ASIL, and so on. Few facts in the beginning, maybe a bit boring, maybe recap for someone. Well, don't leave early. There is the second half is like a practical example of how to evaluate hardware metrics and how the hardware development looks like in automotive safety. So first, what is functional safety? Functional safety is any kind of event that could happen with association with the function of the device of the system. The standard, the basic standard for automotive safety is ISO 26262, and you may be aware of that. This concerns only electric and electronic systems. So if you tear your pens from some sharp edge of your seat, that this is not definitely functional safety. This is personal safety, which does not fall into a scope of that kind of standard. Functional safety, because some hazards are potential for running such systems in cars and in vehicles, then there is a need for reducing such risk of that of happening of that hazard, and this is functional safety basically all about the managing and reducing the risks that are associated. It can be seen in transportation, machinery, medical, nuclear power, and so on and so forth. You may heard that if we separate hardware and software for functional safety, we could see that the hardware and software both have systematic failures or errors in them, and those can be basically prevented by development processes that are in line with standards, rigorous development, testing, traceability, documentation, and basically the quality of the products. Whereas in hardware, there is another additional aspect, which is the random hardware capability, and that can come statistically any time, anywhere. There are some mathematical models how to evaluate the random hardware capability, and based on those, I will talk about those later, we calculate the hardware metrics of any kind of a system. So how do we quantify the risk? We use three letters, ESC. So the risk, as you might know, it's basically a product of severity and frequency. So the severity is the S letter. So what is the extent of the harm, of the potential harm? What is the impact on health, on lives, on environment? How frequently this can happen? So we need to evaluate that one more further. So according to the standard, we need to evaluate also the exposure and controllability. The exposure is how long this operational state durates, how long we are exposed in this situation. For example, how long do we sit in a car every day? That, of course, has an impact. Or how often we use this or that kind of a system in the car. Some of the systems are used all the time while driving. Some of the systems are used just in case of some emergency, some accident. A good example could be an airbag that is used basically only when accident happens, or impact actually, not every accident. And the controllability, that's the last letter. This is C, and this is description or evaluation, how the driver is able to control the situation. Can the driver, for example, press the brake, take the wheel in case of autonomous cars, safely pull over? This is qualitative assessment that basically results in an ASIL level, but more on that later. I also add the failure rate of such a system, and this is basically a target value we want to target, and the tolerable risk is the outcome of such evaluation. So basically, for different kinds of systems, we have different kind of maximum tolerable risk, and all these factors plus the failure rate will be resulting in a defined ASIL, which is Automotive Safety Integrity Level. And this is, well, ASIL, what you probably heard of that acronym, but this is how do we get to this category. This is an outcome from the classification of the hazardous event that potentially may happen. It's specified for a operational mode or situation of the vehicle. Vehicle is high speed, low speed, stationary. It's parked in the garage. Some hazards may happen even in a stationary state, of course. And the classification is done by the letters A, B, C, D. The D is more stringent one. The ASIL classification translates to the safety goals. You may have heard that one as well. Safety goals is a basic vehicle level requirement that is quite generic and is specified for ASIL level. Usually some timing is involved as well. Some safe state is defined for a safety goal, but for basics is enough to see it as a top requirement on a vehicle level. As I said, the safety goal results basically is an outcome of the hazard evaluation. When we identify the hazardous event, we can define what should be prevented, what should be avoided. So usually we use wording like unintended activation of the airbag is prevented with ASIL D classification, or avoid overheating of the system is usually like really simply formulated with no further details. It may contain also a timing constraint. You may have heard about FIT, MTBF, or Lambda. Sometimes those acronyms are used in a confusing way in same context. Sometimes they are used incorrectly, but basically all of those values represent some kind of statistics probability of failure of an either device, like a component, or complete system. The FIT, this is stands for failures in time interval for billion hours of operation. This is pretty simple. The numbers for discrete components or integrated components are ranging from 1 or 0.1 to several hundreds. So it's kind of natural numbers for the components. MTBF stands for mean time between failures. This is basically a legacy from repairable systems that are that you basically predict when the system or part of the system component fails, and then you can repair it or put it back to the operation. For systems like electric or electronic systems, these are usually unrepairable. So the meaning is basically mean time to failure. This is statistic value of a lifetime basically of that system, because after the first failure happens and you detect it, you diagnose it, then you dispose with that kind of with that part of the system. And lambda is basically failure rate is the similar number as the fit, but this is number of failures in 1 hour. So it's in absolute numbers, these are 10 to power minus 8 or something like this. It's used usually for mathematical calculations. There are a few standards that are accepted to evaluate the failure rate of the components, and I took one of them. This is Siemens standard SN29500, and this basically lists some basic failure rates of components, discretes, ICs, and you could see that the more simpler component, the less failures in time can be seen or can be experienced. For very complex MCUs, the base failure rates are around a few hundreds, also depending on the operating temperature. For power MOSFETs, it's important for any kind of power components or components which have significant power dissipation. It's also need to evaluate their temperature increase. So that needs to be taken into account. And very important thing is that any kind of component that contains SRAM, you would need to pay extra attention, because the SRAMs are prone to so-called soft errors, and which may be seen as a bit flip caused by some particle that comes out of space or out of some radiation, which is natural in nature. But this happens quite often, and when the static RAM is not protected by any kind of system like parity or ECC, this failure rates really jumps by orders. So it's like for MCUs, it may reach up to thousands. So also that's why a lot of components containing static RAM already implements parity or ECC. So basic terms like safety mechanisms, diagnostic coverage, and AFMIDA. So I'm using also presenting those acronyms. SM, safety mechanism, is typically a technical solution which prevents faults to become a single point failure. It controls or mitigates the faults that are in let's say intended function of the system. So the safety mechanism does not itself does not contribute to the intended function. So for example, if we have a electric power steering, the safety mechanism does not actuate the motor, does not feed back to the driver. is usually some mechanism that prevents the faults of the primary intended function to become a single point failure. Diagnostic coverage is a parameter of every safety mechanism. It's basically a coefficient ranging from 0 to 1 or 0 to 100%, depending how you look. And the ISO 26262-5 lists a lot of examples of typical diagnostic coverages of typical safety mechanisms. Like, as a very typical example, it could be some voltage supervisor, watchdogs, and so on. ASIL, it's a kind of a work product outcoming when you start designing any kind of safety design. You would need to end up and prove the hardware metrics of your safety design, and usually in a form of a ASIL, which is a spreadsheet listing all the components of the design, all the failure modes of all the components, how the failure modes are covered with safety mechanisms, and the output is hardware metrics, which I'll describe in next slides. Just one more detail, each safety goals basically requires one ASIL spreadsheet. So you need to evaluate every safety goal in terms of the hardware metrics. So what is hardware metrics? It basically quantifies the effectiveness of the safety architecture in terms of how many errors or how much failures are detected, and how many of them are perceived by the driver. Basically, it's all about statistics. So statistically, every component eventually fails, and in order not to become single point of failure of that component, we need to somehow detect this failure and within given time, either put the system in a safe state or indicate this to a driver. So every safety goal has a set of components that are relevant, because not all the components in the system are relevant for each safety goal. So what matters is really those components that are relevant for that safety goal. You do the calculations based on the formulas that are listed in the standard, and there are three key metrics for automotive systems, and this is the probability metric for random hardware failures, PMHF. This is an absolute value which expresses the residual failure rate of a system that sums basically all the rest failures that are not detected. There are single faults, there are not detected faults, or not perceived faults. So for an ASIL system, we could see that the metric is 10 fit. So for a complete system, if any kind of a system that is rated ASIL, for that particular safety goal, you need to comply with this 10 fit value. Then there is a single point fault metric. Single point fault is basically a fault that has a direct impact on a safety goal. So when, for example, a resistor is marked as a single point fault, for example, if the resistor is shorted, it fails short, then it may have an impact on a single point fault metric. So that means that this failure rate of that kind of a resistor counts in the single point fault metric. And this is a ratio of total failure rate. This is a ratio of the single point fault metrics over the total failure rate. So it basically you need to detect all the single point fault metrics, or 99% single point faults need to be detected for an ASIL system. A latent fault metric, in simple words, is a failure rate in the safety mechanisms. So that means that these failures do not have a direct impact on the safety goal. That means when such fault occurs, you don't need to necessarily be exposed to the hazard or to the risk situation, but you should be able to detect such fault and behave accordingly. So it means pull over or repair the car. So functional safety hardware development is according to ISO 26262, is not very different from a good engineering practice. The standard is generally really readable. It's like cookbook-like standard. I would say the most readable standard I ever read. I encourage you to look at it, especially if you're interested in hardware. This part 5 might be interesting for you. As any kind of a hardware that needs to comply with requirements, and it's generally not applicable to functional safety only, but any kind of hardware that needs to comply with requirements is an iterative process. So if you're a junior hardware developer, you would need more iterations to comply with the final requirements of your customer. And regardless if it's a product owner or a real customer, which you need to sell to the product to. But if you're of course experienced, you may assume a lot of things, and from your experience, you can use that experience to decrease the number of iterations. So the hardware development work like you create or modify your schematic, you perform the FMEDA, you evaluate the hardware metrics, and basically if they are not okay, you do the next iteration. And this of course can be done on a paper, but in worst case you need to get back to your schematic design and really reroute your PCB if you see major deficiencies. So now I'd like to show you a really hypothetical and simple example how such iterative process may look like. So the iteration number 0 is the definition of the safety. There is not really an iteration, but it's a definition of the safety goal and setting the functional safety requirement. So I took an example that the safety goal is to prevent overheating of the system with classification of ASIL C. The derived safety requirement already kind of shows the implementation, or from the very helicopter view, it shows how this should be achieved. This may be wish of your customer, that the requirement is activate a cooling fan when the temperature rises above threshold. So this is very simple. We'll start with the first iteration. So the requirements define that there needs to be some fan. We need to detect the temperature, and then something in between. I chose to be an MCU. It could be, of course, any kind of either analog or digital way how to control this sensor this actuator. Let's assume that the MCU is used for multiple functions. This is not only one, so it's probably just one part, just one function that is executed by this MCU. So we need to look on the failure rates of the devices we have here. As you can see that we have just the intended function. We have detector, we have some logic, we have actuator. So let's assume some really basic values. Don't take those too seriously. It's like it may be close to reality, but the orders probably will be realistic. So now let's, according to the scheme, we did our schematic. So now let's look at the metrics. Well, this may be a little bit fast, a lot of new acronyms, but to fit all this information to a few slides, yeah, you might need to look at those slides maybe offline. But anyway, we list all the components in one column. In another column, we list the fit rates, the failure mode distribution. This is basically what kind of failure modes can happen with that component. So if there are some failure modes that are not relevant to our safety goal, we may exclude this. And this actually really happens in case of that MCU. We see that only 50% of the failure rates are relevant for our safety goal. So if we use an ADC, for measuring the temperature, we perhaps do not need a real-time clock, for example. So the real-time clock failures are part of that 50% that are not relevant to the safety goal. And as well for the fan, this is I would say least probable scenario, but only when the fan does not spin when it's needed, then this is relevant. When the fan spins continuously, that it does not obviously harm us. It will just consume some energy. But the residual failure rate is now 56 fit out of total 111, and we see that the single point fault matrix is a ratio, is 49%. There is no latent fault metric, and PMHF, the total residual failure rate, is a full single point fault metric failure rate. Single point fault rate. So obviously there is no ASIL achieved by this. So we need to go to the next iteration. As we've seen, the MCU is probably the bottleneck. It has a lot of failures in time. So we will equip this MCU with an external watchdog circuit. And this watchdog circuit serves as a safety mechanism, SM1, which itself has 10 fit as the chip itself. And according to ISO 26262, regular watchdog has a diagnostic coverage of 90% of all the faults that can happen. So we could see that we have 4 components on the left. We have a safety mechanisms now, safety mechanism SM1, which covers 90% of the relevant faults of the MCU. So the residual fault rate is now decreased from 56 now to 11. So this is a major decrease. But we also have some latent faults, because when our watchdog fails, here you can see that all 10 fit of the watchdog itself goes to latent fault metric, and if the watchdog does not detect this rest of the MCU faults, this goes to latent faults as well, because the driver obviously is not aware of such fault. So that means that even if that watchdog detects the fault, the driver will not do anything because he will simply don't know that something's happened. So he will drive drive on and will not recognize anything. But we can already calculate a next iteration of the metrics. So single point fault metrics has increased to really nice 90% after one iteration. However, latent fault metric is 50%, that's too low number, and PMHF is 66 feet. So it even increased because we added one watchdog. So what do? We need to do third iteration. And no ASIL is achieved, of course. So we add a warning light to the dashboard of the driver. So the driver actually can recognize that something bad happens. So the warning light informs the driver that the MCU fails. Of course, the warning light can indicate any kind of fail, but in our case, this is only the fail that is detected by the watchdog. So this warning light has one fit, and because of by definition, this is a third failure in a row. The third fault is actually not safety relevant according to standard. So we don't need to calculate that in. However, we need to calculate that we will use it in the table as that it does not have any impact on overall metrics. It's even not calculated in the total failure rate of the system. So what we see now that the table is really similar to the previous one, but there is one update. When the watchdog detects the failure, all the detected fails are reported to the driver. So the fault is not latent anymore. So we don't calculate this into the latent fault metric. So the latent fault can happen only in the watchdog itself. So if the watchdog fails, the MCU wouldn't recognize, or it might recognize, but this, we don't go that deep in the details. But in our case, the MCU won't recognize, so full 10 feet of that watchdog goes to latent fault. So that really helped with the latent fault metric, which increased to 90%. Single point fault metric is 90% as well. And PMHF is 21 because we get rid of that latent fault. And this is already ASIL B. However, this was not the requirement. We need to go further and maybe improve some of those values. So we probably need to improve the single point fault metrics, which need to be 99%. So we can look how to improve this, right? We use different type of watchdog that has the same fit value, same failure rate, but it has diagnostic coverage of 99% instead of 90. This is so-called Q&A watchdog, which actually communicates with the MCU through serial interface and basically gives the MCU some kind of like homeworks, and the MCU need to reply with correct answer. So it has a coverage which is definitely better. The ISO 26262 defines it as 99%. And this is still not enough. We need to add another fan which works in parallel with that one, with the first one. Now the MCU concurrently controls the fan 1, fan 2. Those are identical fans. And the identical fan adds 10 feet more, same as the first one. So let's see how the table changed. We of course added the second fan with the same parametrics, but the big change is that the failure of the fan is not anymore a single point fault. So that means that this calculates not in the single point fault matrix. Basically what remains is the temperature sensor and the rest of the undetected faults of the MCU. So instead of 5, we have 0.5 because of the diagnostic coverage. And little negative effect is that by adding this fan, we added also a latent fault because we are not detecting any kind of faults by that fan. We just use the dual architecture with no diagnostic. So any kind of failure in one of those fans counts in the latent fault. Let's see how the metrics changed. The single point fault matrix is nearly on the level of ASIL-D, but it's 2/10 below. Latent fault metric is still, it actually decreased with adding of that one fan more. It decreased, but it's still okay for ASIL-C, and the PHMF is 21.5 fit, which still is okay for ASIL-C. So now we have a compliant design, really simple one. Of course, in reality, you will see much more factors, much more effects, but the basic principles are there. I need to check how much time we have. Yeah, well, probably I will just go through this very quickly. We have different hardware element classes defined by ISO 26262, and these basically depend on their complexity. And these classes, they are divided into 3 classes: basic, intermediate, and complex. This is kind of followed by the support that you get from the component or semiconductor manufacturer. For the most complex devices where you have no possibility to know all the failure modes and so on, you will be provided with a full set of documents, failure mode analysis, failure mode distributions, safety manual, and so on. This is a matter of PMICs, of multi-channel motor drivers, and of course MCUs. These kind of element classes are reflected in Texas Instruments portfolio, and what you could expect from TI. You could see that any kind of functional safety capable, quality managed, or compliant device is listed on ti.com, and you could ask your representative for that kind of a documentation. This table is on ti.com publicly. You could look at it and see where might the component you are looking at falling, which category is falling in, and that basically defines how much effort we spend with extra documentation and effort to support the design. The most complex devices are also independently assessed. Usually third-party authorized body that has processes that could confirm basically the compliance of those components with the standards.